Last lecture we discussed about Ohm's law. We basically have this current density is proportional to the electric field, and this sigma is really the conductivity of the material. It is close to infinity for perfect conductors and is zero for insulators. And we also, from here, we also kind of derived, the normal one, almost now V equals to I times R, where R is really the resistance. We can actually just build a very simple model to really to kind of understand what is the meaning of this conductivity. Okay, so this is called a collision model of conductivity. So now let us, we know that electrons really carry the current, for a normal material. So let us consider that electrons, just travel through a wire, okay? And we know that there are many of atoms, that are inside the wire. So while electrons travel and inside the electrical field, it also collide with the atoms, very often. So in some sense, we can think about that electrons originally speed is zero. It accelerates with some acceleration. It just travels some distance and then hit an atom, and then it reduced the speed to zero, and then it becomes accelerated again. And of course, the directions, is random directions. Okay, so let us for electron, as I mentioned before, the velocity, that due to the electric field, is often very small, is only about 1 centimeter per second. But the really the speed that are due to this is we call the thermal speed, okay, which is actually much higher than the drift velocity, that are induced by the electric field. So we know that from the theorem of equipartition of energy, we have this 2 divided by 3 kBT equals to 1/2 mv thermal speed, okay, square. Okay, so this one, you can learn from statistical course, thermal and statistical courses. Okay, from here, we can calculate this with thermal energy, thermal speed, okay, which is, you see that proportional to square root of the temperature. Okay, so this is what we have. Let us assume that the distance, as I said, electrons start from zero, accelerate to some time, to some energy, then hit the atom, another atom, and then speed reduced to zero. Okay, let us say on average distance. Okay, so this one, you can think about that. This is the distance between two obstacles. Okay, it's just the number, and then the time then it takes. Okay, for it to travel is really the number divided by v thermal. Okay, this is the time it takes, and then the average speed. Okay, and as I said, the electrons start from zero, it accelerated to at, okay, which is acceleration, and then the average then is just 1/2 at. Okay, so then we can put things together. So this will be t is this number, so this is really number a divided by 2 with thermal, okay, thermal speed. Okay, so this is what we have. Okay, now let us consider the current density. Okay, so let us assume this material, okay, have really some how many molecules, okay, per unit volume, okay. And then each of these molecular, okay, have F free atoms, okay. If there are more free electrons, of course, the current will be bigger, okay. And then we have the electron charge, okay. And then we have really just the average speed, okay. Okay, so now if you put the things together, so this is really NFQ divided by is the average velocity is here, where we have lambda divided by 2 V thermal times this A, okay. Let us A assume is really force divided by the mass, okay. And we know that force is really Q times E, okay. So we add together is really NF lambda Q square, okay, times 2M, okay, V thermal times E. Okay, so this is what we have. Okay, so you see that this is the current density, this is the electric field. So this should give us the conductivity. Okay, so the conductivity is really NF lambda Q square divided by 2M with thermal speed. Okay. Okay, and from this very simple model, you can see that when if we have more molecules per unit volume, and we also have many free electrons per molecule, okay, if they increase, of course the conductivity will increase and the resistivity will decrease, okay. And also if the temperature increases, okay, temperature increases, and because we thermal is proportional to square root of T, the temperature, so that really means the conductivity decreases, the resistivity just increases, okay. So you can see that even though this is a very simple model, but it actually pretty good, and it really indicate that agree with the theoretical with the experimental measurements, that you can choose different materials that have different N and F, and you look at the dependence of the resistivity versus N and F, and also people also observed as the temperature increases, okay, and the resistivity also increases, okay. So that it be because the temperature increases, okay. So what happened is temperature increases, okay, the thermal speed also increases, okay, and then the average time it takes, okay, for electron to travel from one obstacle before it collide with another atom or molecule, it becomes shorter, okay, it becomes shorter, and as a result, okay, the velocity becomes smaller, and because J is really proportional to the average velocity, okay, so that means sigma also becomes yeah. Oh, okay, J becomes yes, because this one increases, and this one is resistivity will just decrease. This is sigma, okay, and this rho will increases, okay. And you can also see from the model that I described here, you know. So we have electric field that are applied. So we have electric force. We are trying to accelerate the electrons. But these electrons, as you can see, it will collide with molecules and then lose energy. So in other words, that the work done by the electrical force is converted into heat, okay, because electrons collide with the atoms and then deposit energy there, okay. So you can see that the amount of work, done per unit charge is really V, okay, and the charge flowing per unit time is really I, okay. So then the overall the power delivered, okay, that are due to this electrical force applied, okay, is really P equals to V times I, and because V is proportional I times R, so this is really I square times R, okay. So this is really Joule heating law, okay, where I is really current, and so this is with a unit of ampere, and R, I forgot to say that this has a unit of ohm, okay, which is really defined as the 1 volt divided 1 volt divided by the volt divided by ampere, okay. So then the P has a unit of joule, okay. So this is what we have, okay. So these are, as I said, it is a very simple model, but I kind of to tell you what is really from a microscopic world to see what is the conductivity and what is the resistivity, okay. Okay, now I wanted to this is starting from now I will talk about the electromotive force, okay. So this is really, I wanted to use it later to introduce this the second session, which is about electromagnetic induction. Okay. So now let us assume we have a battery. Okay. We have plus minus two terminals. Okay, and then we have wires, and then we have a bulb here. Okay. Sorry, just a bulb here. Okay, and then they are connected back to the negative terminal. Okay, so this is what we have. Okay, so now when we switch on this circuit. Okay, so let us say there is a switch here. Okay, sorry, a switch here. Okay, so this is not connected. Okay, so connected here, then connected here. Okay, so now of course if we have this switch is on, then the current will almost immediately flows through the whole circuit. Okay. Okay, so you can think about this way. You have, let us say, I have electrons. I have electron. Of course, they are on the wire. Okay. Okay, so once we close, we switch on this. We switch on this. Okay, and then there are electrical field that are in this whole wire. Okay, so then the electrons, each electron that are due to the electric field, the movement is very very slow. However, you can think about that. All these electrons, they move in the same direction. Okay, so then the electric field, you can see that it will be established, instantaneously. Okay, so the charges will start to flow. Okay, there is current start to flow. Okay. Okay, now let us consider a unit charge. Okay. Then the total force that we have, okay, from about since there, okay, for total charge, if we really saying that we have the Fs plus this E. Okay, so here we are really talking about, let me see, I think we are really talking about the, yeah, really talk about the source. Okay, so we're really talking about a charged particle, let us say, um, mm, you know, inside this circuit. Okay, so there are really two forces that are involved. Okay, in driving the current around a circuit that I showed here. One is really Fs, really due to the source. For the example that I showed here, is really just a battery. Okay, and then there is this electrostatic force. Okay, which is really force charge particles to move through the wire, and because here we use the unit charge, really, so Q times E really equals to E. Okay, so this is what we have. Okay, the effect, they are both, one is from the source, one is about the electric field that are created. Okay, so for the force, that are showing here due to the source, and they're different. Okay, for example, for battery is often due to chemical force, and for photoelectric cell, that force is mainly created due to the light, and also for a thermocouple is really the temperature gradient, that will create some force. Okay, that will shows this Fs. Okay, so that is what we have. Okay, so there are two forces, that are applied. Okay, so now let us consider, uh, you know what is the, we have two forces. We wanted to see that what is the letter effect. Okay, around this circuit. Okay, so what we do is we define an integral. Okay, is really this the total force divided by the times the distance. Okay, so you can see that this is really the amount of work, okay, done by this force. Okay, so because this one has two components, so we just do the first integral, and we do the second integral. Okay, and as we know that the electrical field is really coreless. Okay, so this one is really equals to 0. Okay, so in other words that we just have this integral. Okay, so we really just at the end, it really just equals to the work done by the force that are due to the source. Okay, so this epsilon I call it here. So this is called electromotive force. So this is sometimes also written as EMF. Okay, and as you can see here, this is really the amount of work done by this force over a closed circuit. So this is really not, the name shouldn't really is not really the force. Okay, however, this name is so well established, and Griffins still choose to stick with this name. Okay, but you have to remember, this is not really a force. Okay, so this is really the amount of work done by this force. Okay. Okay, let us consider an ideal source. Okay, ideal source, let us consider a battery. Okay, there are no internal resistance. Okay, so that really means this sigma, the conductivity is really infinity. Okay, and of course we cannot really build a battery with no internal resistance. Okay, so just consider this ideal case. Okay, because this battery, is perfect. Okay, sigma is really equals to infinity. So that means really the net force of the source. Okay, let us consider inside this source. Okay, we can consider inside this battery. Okay, and the net force of the source of on all the charges, okay, that are inside is really zero. Okay, okay. So in that case, because f the because sigma is really equals to infinity, so then really the net force is really zero. So that really means the E is really minus Fs. Okay, so E is really minus Fs. So now remember that we can calculate the potential difference, okay, between the two terminals. Okay, let us say the plus terminal and the negative, the minus terminal. Okay, so this is really just the integral. Okay, let us say from point terminal A to terminal B. Okay, we do E times dl. Okay, what do you see that is really becomes A and B Fs times dl. So this is really just the surface is integral over this closed circuit. Okay, which is really give us epsilon. Okay, you see that. So here is really, you can see that is really uh, is really the electromotive force is really used to create the potential difference between the two terminals. Okay, in other words, that batteries have these two terminals, that one is plus, one is minus. So there is really a voltage difference between them. Okay, and it will create the electrostatic field, and this electric static field, will drives current. Okay, through the rest of the circuit. Okay, okay, and then inside the source. Okay, and then the force will make the charge flow opposite to the direction of current flow in the circuit. Okay, so that is what happened. Okay, just look at for a battery. Okay, that is what happened. Is the voltage difference between the two terminals created electrostatic field, and then will drive the current. Okay, through the rest of the circuit. Okay. Okay. So this is what happened. Just show you. What happened for a battery. Okay, it's really, you see that is really the voltage difference is really used, to do the work. Okay, to move charged particles around. Okay, so okay, so here so far we mainly talk about these batteries. Okay, they are very familiar to people. Now we started to talk about this motional, okay, electromotive force, okay. So this is really very important. So this is really called a generate, okay, okay. So this is really you will see that we introduce this concept because we will discuss about the electromagnetic induction. Okay, so this is really it's emotional. Generators really use the fact about motional electromotive force. Okay, so these electromotive forces, they arise when we move a wire through a magnetic field. Okay, so let us consider this case. So there is a region, okay, there is a magnetic field, okay, that is pointing into this page, okay. And now consider that we have a wire, okay, we have a circuit, okay, and then we have a resistor, okay, we often write it this way, okay. So now let us consider the region that are A, B, C, D, okay, that are really inside this magnetic field, okay. And this region, let us say they are outside, there are no magnetic field. And let us assume the height is h, and then this circuit is moving with a speed of v toward the right side, okay. Okay, now let us really just calculate this EMF, okay. So so what do we do is, let us just look at one instant of time, okay. Let us let the time fixed, okay, at a t fixed, okay. And we look at try to look at what happened for the magnetic force that are applied, okay. And you can see that at that time, we should also look at it this way. So the because it's moving, okay. So you can see that so this is the segment AB, okay, and it's moving with a speed of v here, okay. And then we know that it is inside the magnetic field. So then the electrons will have this Lorentz force applied. So that is B is V cross B. V is on the right side, and B is pointing into the page. Okay, so then the really the force, okay, at this moment, okay, the force is really along this direction, along the wire direction, okay. So now we are talking about at this one instant of time, okay. So at that picture looks like that. So we have this magnetic field force, okay, at that moment, okay, it looks like this, okay. and that force, of course, F magnetic here is really equals to V cross B, okay, V cross B, okay. V and B are perpendicular to each other, so it's just V times B, okay. So then the EMF, okay, is really F magnetic field, the F due to the magnetic field times this dl, okay, along this wire, okay, is really here is VB, and because dl is along this direction, is just VBH, okay. For the segment, this BC and AD, okay, BC and AD, because they are not really the horizontal one, they contribute nothing because the force is really perpendicular to the wire, which is the force is still this way, but the dl is pointing along the horizontal way. Okay, so then when you do this dot product, it will have zero contribution. Okay, so this is how we calculate the EMF. Okay. Okay. Now we also remember what we mentioned before. We know that the magnetic field, okay, is not doing any work. Okay, and we said that magnetic forces never do work. Okay, so now the question is, who is supplying the energy, that will create the current, and then of course, will dissipate some heat, on the resistor. Okay, and of course the simple answer is really, the person who is pulling on the loop. Okay, is really doing some work. Okay. So now, we can also just try to look at how to calculate the work done by the person who is pulling this circuit. Okay, so the way to do that, there we can think about this way. So we said that we can the object. Okay, so let us look at the charge. Okay, now we are looking really look at the charge now. Okay, so this charge will have the force. Okay, as I said, the magnetic field force applied, at this moment is just a vertical direction. Okay, so it will cause charged particle to move, and at the same time, okay, this whole wire is moving. Okay, so in other words, that if you look at that particle, okay, it's really moving this, let us say, omega direction. Okay, this is really its movement direction. Okay, at the same time, we know that the force, okay, F pull, okay, is really just the horizontal direction. Okay, so now we want to calculate, figure out what is the amount of work done by this force. Okay, we know that F pull, okay, is really from here. So it's no. So this is yeah. This is okay. So what do we have? Yes. So here what is yes. So here, because here I used this velocity here. So because here we are assuming yeah, it's okay. Yes, because here the electrons are really along this wire are moving with this speed. So then the force is really U times B, is V cross B. Okay, Q V cross B, but Q is really equals to 1 in this case. So F pull is just U times B. Okay, and then we calculate the amount of work done by this person who is trying to pull this circuit. Okay, so the person, you look at the charge, the person is moving this is the force is this way, but actually the particle is really moving along this w direction. Okay, because as I said, it has suffered this electric force, make it move this way, and at the same time it also moves, together with the wire. Okay, and then you can see, let us say this angle is theta here. Okay, so then the distance, okay, so we really is moving this way. This distance is really h divided by cosine theta. Okay, if theta angle is here, and then we do the do the dot product between this F direction and this DL direction. Okay, so this is really give us really this UB. This is the force size. Okay, and then this dot product will give us H size is the DL size is this. Okay, so this is I already did the integral, so I don't need to have this. Okay, this h divided by cosine theta tell us this distance, and also then we need to consider the dot product between this vector and this vector. Okay, so that is really a cosine of this angle, and the cosine of this angle is really is the sine of this angle, which is theta. So it's really give us this. Okay. Okay. So this one really give us this UB times H divided by tan theta. Okay. And U times tan theta is really give us V. Okay. So this give us VBH. Okay. And this one is really equals to the EMF that we calculated before. Okay. Okay. And in other words, that here is really the work. Okay. This is really the EMF. Okay, is really the magnetic field that we are dot this product. Okay, we'll dot this and we get the EMF. And this one really show you the work that are done by the person who is pulling this wire, and per unit charge, of course. Okay, so they are exactly equal to each other. And even though you can see that the integrals that I have done for these two cases, we did it along entirely different paths. Okay, and then there are completely different forces are involved. Okay. Okay, I may not really describe this part very carefully, so I would suggest that you also try to read Griffin's book and take a look. Okay. Okay. So this formula, sometimes you can see that it works very well. Okay, to calculate the EMF, and but however it only works for this rectangular shape. Okay, it's easy to do the calculation. So now, but if there is a different shape, how to do the calculation. So this one is really what we use is called a change of magnetic flux. Okay, so what do we have? We define a function as phi. We define it to be the flux of the B field through a loop. Okay, which is this is the area of a loop. Okay, and that area can have any shapes. Okay, so let us consider this rectangular shape here, and you can see that the area, okay, that is through this loop. Okay, I mean the B field through this loop is really this. Let us assume the distance is x, the height is h, as we said here. Okay, so for this rectangular loop, phi is really b times x times h. Okay, as this loop moves, there are less areas, okay, inside this magnetic field. So as a result, the flux, decreases. Okay, so what is the rate? Is really d phi over dt is really equals to b times h dx over dt, because b and h, they are constant. They don't depend on time. And so this one is really is velocity, is their negative sign. Okay, because it is really it is decreasing. Okay, x becomes smaller and smaller. Okay, because we are pulling out of the magnetic field. Okay, and from here you can see that it's really the EMF is really equals to minus d phi over dt. Okay, because epsilon is VBH. Okay, here we have minus VBH. Okay, so in other words, that this EMF is really equals to minus d phi over dt. Okay, so this is the flux rule. Okay, for emotional EMF. Okay, and it can be proved that this formula holds for any shape of loop. Okay, which is really, this formula is very simple, and also it works for any shape of loop, which is really great. Okay, so that's all I want